and welcome to Africa Teen Geeks Online School. Yes, this is the STEM Digital School, and I hope that everybody is here and waiting to do some physical sciences for grade 12. Yes, I know you guys are all doing matric, and this is the time, where you can get all your preparations ready at home. So you don't necessarily have to be at school because it's much safer to be at home anyway. So if you do get a chance, just be at home and let's work here on Africa Teen Geeks. And we have got you here to do yourself some physical sciences. Yes, indeed, my name is Nonkululego Matondo. I am your physical sciences grade 12 teacher. So it's the 2nd of July. And yes, from yesterday, we started off with the work, energy, and power. And we've been moving on from there. And today we're going to be doing work energy theorem. Okay. So I hope that everybody is ready and is prepared. And guys, it's always great, that you do some stuff before class in order for you, to at least know what questions to ask when the class commences and wherever you're getting stuck to be clarified. But nonetheless, this is a class, and I'm glad that you guys are all here, reminding you that I'm working from the Siavula and Study and Master textbook, and which I've gotten absolutely free from Snaplified. So if you would like to get some more textbooks, especially when it comes to grade 12, you just need to study a whole lot of things, right? I know. So Snaplify is an app that you can download, and there you can get your free textbooks. They are free for the rest of the year until the 31st of December because of the COVID-19 problems that are happening this year. So you can go and get yourself some textbooks, not just physical sciences, any other textbook. So that Snaplify is the application for you. Can even get it on your hand devices, which is your cell phones, and you can get all textbooks that you need right there. Okay, so before we get started on today's lesson, I would like us to go to our homework. Okay, I hope that you guys have done your homework like I asked you to. So the homework is from your Siavula textbook as well. We already did number 1, so I just cropped it out and I started from number 2. So number 2 says a 10 Newton fractional force so sorry slows a moving block to a stop after a displacement of 5 meters to the right. Okay, the block has a weight of 20 Newton. Determine the work done by the following forces: the normal force, the weight, and the frictional force. Okay, so the first thing that they did here was draw themselves. Okay, this structure is what was given, right? I hope that you guys did this homework. So the normal force is this one, and the gravitational force is this one, and the frictional force is this one. So what does this mean? Remember what we said. For us to calculate the work done, we always take the force that is parallel to the displacement. Displacement is here, and then the frictional force is there. So what does this mean? It means that the frictional force is the only force that we're going to be using to calculate the work done, because this one is perpendicular, we don't calculate it. And this one as well, it's also perpendicular, which means we will not be calculating it. So you just calculate the frictions, you go straight to the friction. And so the friction, because it's opposite, remember I told you guys that whenever it's either negative, if they say talk about a frictional force or opposing force, you know that it's either you're going to change this to cos 180, or you're just going to automatically know that it has to be a minus. But it's always best to write it fully like this, just to make sure that you're doing the right thing. No shortcut, guys. This is your matric. You don't know who's going to be marking your script, so always make sure that you give as much detail as you can in your answers. Okay, so hence here you can see it says cos 180. It wasn't given to you. It's something that you should know because it's frictional force. It talks about a frictional force. So what are we going to have? Our normal force is going to be 0. Our weight is also going to be 0 because it's perpendicular. And the only weight force that we're going to have, work done, is the frictional work done because it's minus 50 joules. Okay? I hope you guys got it right. Okay? So, going to number 3. Number 3 says a 10 Newton force is applied to push a block. You see? Already we know there's a frictional force because they talk about pushing. Remember, I said it's pushing, opposing, or frictional force. All these 3 things, they mean the same thing. They can either say push, frictional, or oppose. So those are the 3 definitions of friction. Okay? So a 10 Newton force is applied to push a block across the frictional surface at a constant speed for a displacement of 5 meters to the right. Okay, so say the block has a weight of 20 Newton and the frictional force is 10 Newton, which is already was told to us there. Determine the work done by the following forces: the normal force, the weight applied force, and the frictional force. Okay, so this is what we have here. So this is the force applied and this is a frictional force. Okay, yeah, a force is applied to push a block. Okay, oh yeah, the force applied to push. So in a way it's just the same as pulling because you're pushing it on a direction that you want it to go on. So it's a force applied, that's why it's the side. But then we've got the same force in the friction side, which is a 10 Newton. So what does this mean here? It means here that we're only going to have 2 forces that we're going to calculate for the work done. We're going to have the frictional force and we're going to have the force applied because they're both the only 2 that are perpendicular to the displacement. And this one, I mean, they're the only 2 that are parallel to the displacement. But for the normal, for the N and the gravitational, we're going to have it as 0 because they are perpendicular. Okay, so let's move on. So you see here we already calculated the frictional force this side, which, don't forget, the 180 degrees, and this will give us minus 50 joules. And then for the applied force, this one, you see you do not have the cos 180 degrees anymore. Why is this a 1? Because it's cos 0. Cos 0 is equals to 1. And why is it a cos 0? Because there is no angle. As you can see here, this one is just a straight force. If it was at an angle, for example, at an angle of 30 degrees, that's where we would have plotted our angle, which is this one here. So here's just a straight up force applied, 10 times 5, and it gives you 50 joules. Okay. So, I wish we had done the net force because we'd be able to calculate it now. So that is our answer. So for the normal force, it's 0. For the weight, it's 0. For the frictional force, it's minus 50. And the applied force is 50 joules. Okay. I hope that you guys are together. If you guys are getting stuck, I forgot to tell you guys, you could always send me a chat and I'll attend to it as soon as I can. And wherever you're getting stuck, don't wait for me until the end of the lesson. Whenever you're getting stuck somewhere you don't understand what I said, just send me a chat and I'll explain it quickly. Okay? We don't want anybody to be left behind. We want some A's. So, an object with a weight of 20 Newton is sliding at constant speed across a frictionless surface for a displacement of 5 meters to the right. Okay? An object with a weight of 20 is sliding. So this one has has no force that's pushing it. Okay? So it's just sliding. It's like putting something on a, on an inclined position and it just slides on its own. Okay. Determine if there's any work done. But if then you look at the block here, you see this block, we only have 2 forces there. We have the normal force and we have the gravitational force. And these 2 forces, we do not have any frictional force, we do not have any applied force. So which means we only have perpendicular forces. And what does that mean? That means that we do not have any work done on this um, question. So no work is done as all the forces act perpendicular to the direction of the displacement. Okay? Are we together, guys? I hope that we are. So moving on to number 5. Number 5 says that an object with a weight of 20 Newton is pulled upwards at a constant speed of 20 Newton as a force for a vertical displacement of 5 meter. Okay, an object with a weight of 20 Newton is pulled upwards at a constant speed of 20 Newton, a vertical displacement of 5 meters. Determine if there is work done. Okay, so this one, you see what is happening here, guys. This one, there's a difference between these two problems. These two problems was, this one was sliding down, so there was no force, and the displacement is horizontal, right? So the displacement here was horizontal, so we needed the horizontal components for us to calculate the work done. So with this one, in the case of this one, our displacement is vertical, okay? So which means that what we're going to consider, we're going to consider the vertical forces for the first time. This is different from the other problem. As you can see, force for a vertical displacement. You must always read your question, guys, because physics is very, very tricky. So this one is a vertical displacement, and so which means that you're going to calculate the usual perpendicular forces are the ones that are now parallel to the vertical displacement. So which means we're going to have the work done on the tension, and we're going to have the work done on the gravitational force as well. Okay, so this is what we're going to get. It's going to be F triangle X cos theta. Work applied is going to be 20 times 5. It's going to be 1 because cos 0 is equals to 1 because we do not have any angle here. It's just a straight up vertical inclination. Okay, so this is going to give us 100 joules. And then for the gravitational force is going to give us this, and it's going to be 180 degrees. Why is it 180 degrees? Because it's 180 degrees out of phase. Okay, this one is 0 degrees, this one is 180 degrees. Do you guys understand? Okay, I hope that you do. So that is why this one now becomes an opposing force, and that will give us minus 100 joules. Okay, so that is it. I hope that everybody has gotten their questions right, and they slowly starting to understand what is happening here, with objects and the work being done on an object. Okay, so now we're moving on. So what are we going to be doing today? Today, we left something behind yesterday. We left out the network, because now we've only been doing work on an object, okay? A single force on an object and calculating different forces. So now today we're going to do the network, and thereafter we're going to do the work energy theorem, whereby we need to know the difference between conservative and non-conservative forces. We need to understand the result of a net force working on an object. We need the application of the work energy theorem to objects on a horizontal and inclined plane, and the calculations of different motions of objects. Okay, so let's get to network. Okay, network done is the total force that is acting on an object. Okay, so like before, we had an object, and we had different forces pointing in different directions. Okay, we were calculating individual forces at that time. We were not calculating the net work done. So what the net work done is, the net work done is the total of all these forces. So basically, it's still going to be the same thing, but now we're going to need to combine them together and have one set of answer of the network, okay? So when there is multiple forces acting on an object, we can be required to calculate the net work, okay? This is important because we need to understand that when a force is acting against an object, it's a frictional force and it will usually have a negative sign. So when calculating the net work, it's very important that you get your signs right. Don't forget, guys, when it's opposing or friction, it has to be at cos 180 degrees, or you can just, but your answer has to be negative, okay? So in order for us to calculate the net work, there's two methods that can be used to calculate the network. The first method is we calculate the work done by individual forces. In this case, the signs need to be taken into consideration. We add the results from individual work done with their signs, and that will be the net work of the calculation. So calculate work done on both parallel and perpendicular forces. So as much as we usually don't get zero on the perpendicular forces, but you need to calculate it just to make sure, because that's how method one works. You calculate all the work done, okay? And then for the second method, we calculate the resultant force. First, you need to have your force diagram, which is this one right here. This is your force diagram, as you can see it here. Thereafter, you calculate the total resultant force. When calculating the work done, be sure to consider the angle of normal force if it's applicable, okay? Do you understand? So which means that once you have your resultant forces, you will go and now calculate the work done, and you're going to use, if for example, your normal force is at an angle, you're going to have to take that angle there and plug it into your equation. So calculate the forces parallel to the displacement only, okay? As usual. So I want us to go and check some examples from our Siavula textbook, because I wanted an example where there is both the methods, okay? Okay, you should be familiar with this problem because we did it, remember, first, but it wasn't as detailed as this one. So now it's the same, it's a worked example for approach one, okay? So we're going to have two approaches, okay? So the question says, the same car is now accelerating forward, but friction is working against the motion of the car. A force of 20 Newton is applied forward on the car while it is traveling 20 meters forward. A frictional force of 100 Newton acts to oppose this motion. Calculate the net work done on the car, okay? So what do we know? Only forces with a component in a plane of motion are shown on the diagram. No work is done by Fg or F normal as they act perpendicular to the direction of the motion. Remember, so which means that here we've got our F applied, F friction. On top here we'd have our normal force, and down here we would have our gravitational force, but we do not consider them because they are perpendicular to the displacement, okay? So how do you apply the first method now? For the first method, you analyze the question to determine the information provided. So we've got the force applied, which is 300. We've got the frictional force, which is 100. We've got the displacement, which is 20 meters. And the applied force and distance moved are in the same plane. So we can calculate the work done by the applied forward force and work done by the force of the friction, okay? So these quantities are all incorrect units. Okay, so always, guys, make sure that your units, you are in check and you know that they are correct. Okay, so now we analyze the question to determine what is being asked. We are asked to find the net work done. We know the definition of the work done is W times Fx cos phi. Okay, then on step 3, next we calculate the work done by each force. Remember in step 1, method 1 or approach 1, we said that that is where we calculate the work done on each one of the forces, and then when we add them together, we will get our answers, right? So the work applied here, it's going to be 0 degrees, it's going to be 300, and it's going to be 20, and it's going to give us 6,000 joules. And for the friction, we're going to do the very same step, but remember, guys, cos 180, because the friction is 180 out of phase from the applied force. It's an opposing force, okay? So it's going to give us minus 2,000. So now, when we calculate the work net, we need to add these two together, but you add it with the sign that it comes with, okay? So now it's going to be 6,000 minus 2,000, and that will give you 4,000 joules, okay? The answer shown in this worked example shows that although energy has been lost by the car to friction, the total work done on the car has resulted in a net energy gain, okay? This can be seen by the positive answer, okay? Are we together on method 1? If you're getting stuck, let me know. I'll go back, okay? So now we're going to the second approach. The second approach, if you guys remember properly, we said we're going to find the resultant forces, okay? And how we're going to do that, we're going to only calculate the forces that are applicable to, that are parallel to the displacement of the object, okay? And when we do that, after we get the resultant force, now we can go back and plug it into our work done equation, and we can get the answer from there. Okay, you guys remember that? I hope you do. So now let's get to it. The same car, you see, is now accelerating forward, which is the same question as the one before, but now we're going to have a different approach to how we're going to calculate the answers, okay? The applied force F applied and the force friction 100 are in the same plane as the distance moved. Therefore, we can add the vectors. As vectors require direction, we will say that the forward is positive and therefore backward is negative. Note, the force of friction is acting at 180 degrees, and so is acting the opposite vector direction is negative, okay? So we're going to analyze the question. This is what we're going to have. This is what we're going to need to have. So now we're going to calculate our force, our net force, okay? In order for us to calculate our net work done. So first, we're going to draw the force diagram. Like I mentioned to you guys, that the force diagram, it's very important that you always have it, because it's going to help you in determining what is what. And in some other cases, you will never know. Probably your first diagram is also going to be, you might be getting marks for it. So now let's think about it. Our F net is going to be 300. Our force applied is going to be 300, which means it's going to be a positive. And our force friction is going to be a negative 100. Why is it a negative? Because it's opposing the applied force. So our F net is going to be 200 Newton forward. Please, guys, always mention direction, okay? Always mention the direction. So F net is pointing in the same direction as the displacement. Therefore, the angle between the force and the displacement is going to be theta is equals to 0 degrees, okay? We do not have a inclination. So then we're going to calculate our work, our net work done. So we're going to use our net force, which is the 200 we got here, times by 20, which is a distance, and times by cos 0, because there is no angle. There is no angle that was given to us. So this all in all is going to be 4,000 joules. Okay. So what does this mean? You see, this 4,000 is exactly the same as the 4,000 here that we got on our method 1. So your answers, they have to be the same if they are correct. If your answers are not the same, it means there is somewhere where you went wrong. So you can always try and do both methods if you're a fast writer and you want to check if your answers are correct. Okay. I hope that you guys understood what is happening in here, and you'll be able to do other problems. Okay. So let us go back to our slides. So that was it with the net work. Okay. It's quite simple, isn't it? It's the same thing that we've been doing. The only difference is that now you just have to add them all together and get an answer. Okay, so now we're going straight to the work energy theorem. Okay, so what do we need to know before we get started? Is that energy is calculated in joules, is a scalar quantity, just like work. Work is also a scalar quantity that is defined as the capacity to do work. Okay, that is energy, is a capacity to do work. Many types of energy exist, okay, in the environment that you know of. Maybe no potential energy, kinetic energy, electrical energy, heat energy. There's many energies, but in the work energy theorem, there's three specific energies that you're gonna need to know and that we are gonna be working with. The first one is gravitational potential energy. The second one is kinetic energy, and the third one is mechanical energy. What is gravitational potential energy? Gravitational potential energy is energy stored in an object as a result of its vertical positioning or height. The energy is stored as a result of gravitational attraction of the Earth for the object. Okay, so this is where we get to EP is equals to mgh, and G, we already know G, it's 9 times 8, 1 times 10 to the power minus 3. Yes. So these are things that you guys, minus 2, yes, minus 2. So these are things that you guys have to know. So that is a gravitational potential energy. It's a vertical energy, basically. If we want to summarize it, we can say it's a vertical energy. So then you also have the kinetic energy, which is the EK. This is the energy that an object possesses due to its motion. A force acting on an object can either increase or reduce the kinetic energy. Okay? You guys see that? So the kinetic energy is equals to half mv squared. So kinetic energy has all to do with movement, with velocity, with speed. Okay. I hope that you guys are still following. So that is our kinetic energy. And then the third one that we're going to be dealing with is the mechanical energy. So what is the mechanical energy? The mechanical energy is a sum of potential energy and kinetic energy. Okay? Are we still together? So let's move on. They say when calculating forces, it's important to know whether it's conservative energy or it's. Can everybody hear me? Can you just okay? Energy theorem. Um, Let me just turn this into a proper slide. Okay. Okay. So when calculating forces, it is important to know whether it's conservative energy or non-conservative force or a non-conservative force. Sorry about that. This information allows us to know whether the force will change the object's total mechanical energy or not. What does that mean? Okay, let's quickly go to the theory of behind conservative and non-conservative forces. Okay, a conservative force is the force whose work done is independent of the path taken and only depends on the initial and final position. Okay, so it will always be y1 minus y0. Okay, an example of this is the gravitational force, electrostatic force. Those two are good examples of conservative forces. For example, a person can take a lift to go downstairs, but they can also take the stairs. The gravitational potential energy of the two will be the same. They are not dependent on the pathway. It's all about where you started and where you ended. And that's why that is a conservative force. So when we work with conservative force, we work with potential energy, and that's why we have the mg triangle y. The change in y is where we get to when we talk about the initial and final position and initial position. Okay, so if we had to do this one, as you can see here, if we had to calculate the work done on this on this beautiful lady going up and down the stairs, for the first time, a will be y1, it's going to be 0, and b will be y final. Okay, this is y initial, and this is y final, but you can also say y1 and y0. Okay, but for the second time, y1 is the height where they ended in, and the y0 is going to be the final one. So when you do when you calculate the work done, it's going to be minus mg y1 minus y0 plus mg y1 minus y0. And this will give us a minus mgh plus mgh, and that will give us a 0. Okay? Do you guys understand what the conservative forces are about? I hope that you do. Okay? So then we move on to the non-conservative forces. The forces whose work done is dependent on the path taken. For example, frictional force or air resistance. Friction can permanently take away energy from the body. This causes the total amount of mechanical energy to change. So which means it's either going to be more or it's going to be less. Okay? So no potential energy can be defined to them. Okay? Are we together, guys? I hope that we are. Then, going back to the work energy theorem. What is the work energy theorem? The work energy theorem states that the work done on an object by the net force is equal to the change in its kinetic energy. Okay? The work energy theorem states that the work done on an object by the net force is equal to the change in kinetic energy. So there we have it. We've got work, the net work, then we've got the kinetic energy, then that is equals to the change in the initial kinetic energy minus the initial, the final kinetic energy minus the initial kinetic energy. Okay, so the net work is a sum of work done by non-conservative forces and conservative forces. Okay, so what will we have? Our work net will be work non-conservative plus work conservative, and then you change the KE. The change in KE will give us the work non-conservative plus work conservative. So if you check here, the non-conservative, it will probably be your forces, which is the the frictional force and the air friction as well, and the work conservative will be your potential energy. Okay, so there's some examples that I wanted us to try out, but let me check if we still have time. I think we can still do one example. Let's see, where are these examples? Okay, we've got on page 232, on the Siavula textbook, the Siavula or Study and Master. Let's see, page 232. Okay. Okay, I'm just trying to find the textbook that we are using for this problem. Okay. So, page 232. Okay, we just have 5 minutes left. I just wanted us to do a quick one. Okay, here's one question, which says that a 1 kilogram brick is dropped from a height of 10 meters. Calculate the work that has been done on the brick between the moment it is released and the moment when it hits the lifted. Okay, so now we determine what is given and what is. Yes, it's 1 kg. The initial height of the brick is 10 meters and the final height of the brick is 0 meter. What we are required to determine the work done on the brick as it hits the ground. Okay, so we determine how to approach how to approach the problem. Okay, so the brick is falling freely, so energy is being conserved. So we know that the work done is equal to the difference in kinetic energy. The brick has no kinetic energy at the moment it is dropped because it is stationary. So when the brick hits the ground, all the brick's potential energy is converted to kinetic energy. Okay, so now we determine our potential energy, which will be mgh. Okay, and then after we determine the work done on the brick. So now that we have the potential energy, now we have our potential as 98, but we have our kinetic energy as 0. So from the work energy theorem, now we're going to say work net is equal to change in kinetic energy, and that will be the kinetic energy final minus the kinetic energy initial, and this will give us 98 minus 0. Okay, so hence 98 joules of work has been done on the brick. Thank you guys so much for a beautiful lesson. Our time is up. So homework for tomorrow. Let me see what can we do for tomorrow as homework, just to keep our minds busy. Okay, quite a lot of examples here. But you know what? I think maybe tomorrow, because I see some people have been disconnected and they're unable to connect back. Let's do some more problems. Let's do 2 more examples of the work done, work energy theorem, and then we can continue with our work, and then we'll see if we can have an example that we work with from there. Okay, thank you guys so much for being the best guest ever and joining this classroom. This is a physical sciences grade 12 classroom, and we haven't completed what we wanted to do, but I think tomorrow we will start with the work that hasn't been done first, because we stopped here and we still had some other work that we had to do. Okay, so but for now our time is up, and thank you.